Hi guys, hope all of us are doing fine. My name is Ernest and this is Ernest Sciences and Mathematics TV channel. I'd like to welcome each and every one of us into my discussion for today. I'm going to look at matrix algebra, and this is going to be a second part of our previous discussion where we had a range of ideas on the concept of algebra, and we had looked at how we can represent basically the concept of matrices in terms of definitions, the different types of matrices, and of course how we can identify the various elements of a matrix using either a null, vector, diagonal, or upper and lower triangular matrix. In this particular case, I'm going to look at the basic concept of equality of matrices. We shall also look at addition and subtraction of matrices, and also the scalar multiplication of these specific matrices. In my previous discussion, I had basically indicated that a matrix is going to be an ordered rectangular array of numbers that are going to be either represented using the closed brackets or the parentheses. And in this case, we said that we can have different types of matrices in terms of orders, which we defined using the ith row and the jth column. And these are going to be forming basically our general way of trying to present this specific case of matrices. So we said that we can have different types of matrices ranging from a square matrix, and then of course we talked about this null or a zero or null vector, and then we talked about the concept of an upper or a lower triangular matrix, and whose special case, of course, we had talked about the concept of an identity matrix, which we gave in terms of an example. So in this case, we are going to look at various operations which we can perform for these specific matrices, and they are going to give us a range of characteristics which we are going to witness for different types of matrices. So in a sense, we are going to also to see that different matrices are going to be having, of course, specific characteristics which we are going to be, of course, associating with their various range of different operations. And these are going to constitute particularly addition, subtraction, multiplication, and a scalar multiplication of other types of matrices which we are going to use as our examples. So we are going to look at the concept of equality of matrices, and this basically is going to be assisting us in trying to identify a way of showing that basically two matrices which can be given as either A or B are of course equal. Now if we take those specific types of matrices as our general example, so A and B, which are going to be forming matrices, are said to be equal if they are of the same size or order. So I'm just going to give these ones in summary forms so that we can be able to conserve on space. So A and B are going to be equal matrices if they are going to be of the same order. And we had said that we can give an order of the matrix in terms of of course, mth row and nth column. And these are going to be represented as either an ith row or a jth column. So in any case, if we mention the column, then therefore we're going to just be using this designation for j and a row for I given as such. So an order, a matrix of order m by n, which are of the same order, particularly if I may give an example of a 2 by, of course, a 3 matrix, or a 3 by 2 matrix. This matrix is going to be represented as of the same order if we are going to have these specific values for I, of course, and the jth column equivalent to matrix B, which is going to be consisting of ith row and jth column given as such. And this is going to be, of course, a situation that is applicable for all values of ith columns and jth rows. And of course, for all values of I and j which are going to be obeying this specific, of course, concept, and therefore are going to imply that we are going to have these matrices which are going to be equal. So in a sense, we can look at this specific type of matrices, and we're going to treat equal matrices by considering their corresponding entries which are going to be considered to be equal. Therefore, we shall look at an example which is going to be assisting us to try to do this specific evaluation of a matrix which can be given in terms of x plus y, which are going to be a known value making the first entry, over that specific row or column. And then we're going to have x minus y for the second row given as such. And then we shall have another one over 2s plus r, making the second entry for the first row and making the first entry for the second column given as such. And these are going to be given as equivalent to the values of 4, 6, and 2, 3. So therefore, we said that for an equal matrix, where they are going to be consisting of this specific kind of course, a relationship, whereby if we have this one as A and B, then we can say that all the elements of ith and jth columns of this specific matrix is equivalent to all the elements of j and ith of their corresponding entries. And therefore, what we shall do is try to solve this specific, of course, range of values for the value of x, and then we are going to look for the value of y, s, and r in that specific order. So in this case, we are going to have their corresponding entries given as such. So x plus y is equivalent to the first entry of this specific matrix. And then we shall have another equation of these specific terms, which are going to be x minus y is equivalent to this lower part of the equation. So we solve this one simultaneously and find this one equivalent to. So this is going to be plus 2y is equivalent to 2 given as such. So the value of y is equivalent to 1. So we're going to take this one of these equations and have it given in terms of x plus y is equivalent to 4. So that implies that we're going to substitute for y and have it as x plus y, which is 1 is equivalent to 4. So implying x is equivalent to 3. And therefore, we're going to have the two values of y and x given as such. So for the second, of course, a column which is going to be forming the elements of s and r, as well, we're going to use the same strategy in trying to find these specific corresponding entries for their known values. And this is going to be the second column, the first entry, which is going to correspond to 6. And for the second one, it's going to be the second column, the second row corresponding to this specific entry of 3. So we will have perhaps if we have an addition of that one, so we shall have an addition of that one. This is going to be 3s plus 0 is equivalent to, this is going to be 9. So we shall have 3s equivalent to 9, and the value of s therefore is equivalent to 3. So we shall have this one given in terms of 3 given as such. And of course, we can take this specific value of s minus r is equivalent to 3, implying that 3 minus r is equivalent to 3. And therefore, the value of 3 is equivalent, or rather the unknown r is equivalent to 0. And those are going to be giving us the corresponding entries for those specific types of matrices which we have given in terms of this particular arrangement. So that's going to define in a way the equality of matrices. And we're going to treat equal matrices of different types, which are either consisting of known values for the respective entries, and try to find their respective values using the same entries as I've just done on the board. So we're going also to look at the concept of addition and the subtraction of matrices, and see how we can perform various operations for this specific type of matrices using the two types of basic operations. Now, in this case, we are going to have this specific set given as such. Now, suppose we have matrices A and B, which can be given using the capital letters. Let A and B be matrices which can be defined as such, or matrices of order M n given as such. And these matrices are going to be, of course, of the same order. Now, in this case, we are going to have this specific order being the same as we said. So we can have an addition of this particular matrices or a subtraction of these matrices given as A plus or minus B is equivalent to the elements of A, I, J plus the elements of B, I, J given as such. And we're going to be adding the corresponding entries for the ith row and jth column as I've just done from my previous example. So this is going to be giving us a value of another matrix which is going to be C, particularly of having the same, of course, order of the two specific individual matrices which are given in terms of n and m given as such. So we can give a general example of this one and try to see how we can perform an additional subtraction of this specific matrix using what we have basically defined. So given a matrix of this specific kind given in terms of OK and 4 for the first row, and then we're going to have R7 and 2. So this is going to constitute of specific values and of course unknown values of this specific matrix. And if we have that one added together with D, perhaps that's going to be forming 5, 6. And then we have 3, 2, E given as such. And this is equivalent to the values of 7, 8, 10 for the first row. And then we shall have 5, 9, 3 for the second row given as such. So this implies that the addition of the two corresponding entries for the matrices which are going to have on the left side of this equal sign is going to be equivalent to the sum of these specific individual entries of the result which we have given of the corresponding matrix. So in this case, we shall have a way of finding these specific values of, so we are going to have D, E, K. So we have R, D, E, K, and R given as such, and try to see how we can use that specific ID for finding these specific entries. So this implies that we're going to have the first entry for the first, of course, matrix given in terms of 0, plus the corresponding entry of the subsequent matrix given in terms of D is equivalent to 7. So this implies that the value of D is equivalent to 7 given as such. And if we have K, we are going to take a corresponding entry for 5, which is equivalent to this specific part of the matrix, which is going to be given as 8. So this implies that basically K is equivalent to 3, and we're going to have this one given as such. So if we take the value for R plus the corresponding entry of 3, this is going to be equivalent to 5. So this implies that R is equivalent to 2, and we're going to have it given as such. So if we take for E, we are going to have 2 plus E. So this is a corresponding entry for E is equivalent to 3. So this basically implies that the value of E is equivalent to 1. So using this specific analogy, which we have just defined for addition or subtraction of matrices, this is going to be assisting us trying to evaluate a various range of matrices which we are going to come across in our subsequent discussions. So lastly, we shall look at the concept of a scalar multiplication of matrices, and that is going to be forming, of course, our last bit of this specific discussion in trying to find out how we can represent matrices in terms of their scalar multiplication. So we're going to use particular examples, and I have a general way of trying to, of course, determine this. Now, suppose we have a matrix, two matrices defined as 7A plus perhaps 8B, but we're going to have this one given in terms of perhaps 6B. So we can find this specific matrix by defining the matrix of A and B and having a scalar multiplication of 7 given as such. And now in this case, if we have a matrix which is going to be given in terms of A is equivalent to this 1, 3, 4, 2, and then B is given as a matrix of course, 3, negative 2, 7, 4. So we can see that these two matrices are of the same size or order given as Mn, which is a 2 by 2, 2 by 2 matrices given as such. So therefore, we can perform an operation of additional subtraction as per our previous definition. So we're going to have 7A plus 6B given in terms of 7 into 1, 3, 4, 2 plus 6 into 3, negative 2, 7, 4 given as such. So we're going to multiply each of these entries of the respective matrix with this specific quantity which you are given as a scalar of 7 and 6. And this is going to be giving us the values of 7, 28, 21, 14 for the first matrix. And then we're going to have 18, 42, and then negative 12, 24 for the second matrix given as such. And this whole, so kindly do your evaluation from the other side and see whether you are finding the same values. So I'm going to get 25, 9, and then I'm going to have 70 and 28. So this implies that I'm going to perform an addition of each corresponding value for the subsequent matrix from the scalar multiplication. And these are going to be giving us the various entries for representing the M and N given as such. So in this case, this is how we can perform a scalar multiplication of various types of matrices, which we are going to come across in our various evaluations. So kindly check our description boxes for various links of other videos. Engage us in the comment section and also ring that notification bell for a various range of updates on different discussion in math and sciences and other areas of application. So that is it for now, guys. Bye. God bless you. Catch us in our next video.